Thank you very much. Last time I explained the construction of this essential skeleton, which was a canonical skeleton sitting inside our Berkovich space. And today I want to explain first the relations with minimal model program, and then an application in a quite different domain, at least at first sight, so in the theory of Igusa's p-adic zeta functions. So that has a more number theoretic flavor, and then we will finally see some positive characteristic, even if it's kind of a fake. But we'll get to that a bit later. So first, I'll explain the relation with MMP. And then I have to impose a couple of extra conditions on the varieties that we are working with. So X will still be smooth. Now I'm going to assume projective to be able to run MMP and geometrically connected. K variety. And so what we did last time, for any choice of non-zero pluricanonical form on X, we defined the associated weight function on the Berkovich analytification. We looked at a locus where this weight function was minimal, so we got this skeleton which was defined by Kontsevich and Soibelman, attached to X plus some pluricanonical form. And then by taking the union over all non-zero pluricanonical forms, we got the essential skeleton. And so I already mentioned then that in order to get a sufficiently large object, it's important to have enough pluricanonical forms. And it turns out that the correct condition to impose is that the canonical line bundle is semi-ample. So that's an additional assumption that we are going to make. So some tensor power is generated by global sections. And so the results we proved last time already are a big step towards understanding this essential skeleton, because at least it tells us that whenever we pick any DLT model we like, the essential skeleton will always be a union of faces of its Berkovich skeleton, of its dual intersection complex. So it tells us that the essential skeleton is a reasonable object, but it's not very useful to understand its precise geometry, because in principle, we would be obliged to test every possible pluricanonical form and see where the weight function becomes minimal. So under this assumption, it turns out that MMP gives you a way to compute the essential skeleton in one step, namely by looking at the minimal DLT model. So let me first recall the definition. So a DLT model of X is called minimal if the relative canonical, well, this is not necessarily a line bundle, but at least it's a Q line bundle, so it still makes sense to say that it's semi-ample. Yeah, so also on the model, this canonical extension of the canonical line bundle on X still has plenty of global sections, at least after taking a suitable tensor power. And then an important and very deep fact, which is a result of collective efforts of many people working in the MMP, is that minimal DLT models exist. With a small caveat. So let me write plus minus. What do we really know, to be precise, is that if our variety X and the model curly X are defined over an algebraic curve rather than a formal power series ring or a Laurent series field, then this is what you get by starting from any SNC model and running an MMP for the SNC model and its reduced special fiber. So unfortunately, the way MMP has been written down in the literature, it doesn't apply directly to the case where the base is a ring of formal power series. So although, I don't think there's any serious obstruction, there's no suitable reference that covers this case. And so in the case where we cannot assume that x is defined over an algebraic curve, you can do something which for our purposes is as good as producing a minimal DLT model, and that's producing a minimal QDLT model. So this we proved in a paper with Janos Kolar and Chenyang Xu. So I'm not going to explain what is the definition of QDLT, and for all purposes here, we can just accept this as a true fact. If you really want to go into the details, there's a small thing you have to take into account. But that's where the plus minus comes from. And so how does this help us to compute the essential skeleton? So we have the following theorem, which was part of joint work with Chenyang. So if curly x is a minimal DLT model of x, so I write because, well, as you probably know, minimal DLT models are not necessarily unique, but we just pick one. Then its Berkovich skeleton is equal to the essential skeleton. And so it makes sense to say that these two objects are not only homeomorphic, but even equal, because they both live inside the Berkovich space Xn. So the proof, well, with all the work that we have done so far, the proof is pretty straightforward. The implication from left to right is something which we've already proven. We've already observed that whichever DLT model you choose, the essential skeleton will be a union of faces of the skeleton of your DLT model. So this is what we did yesterday. And then, well, for the other inclusion, minimality becomes crucial. We have to show that every phase of this guy is included in the essential skeleton. So we know that the faces correspond canonically to the strata of the special fiber of the DLT model. So we take any stratum. And now we use the fact that the relative canonical bundle is semi-ample. So we take omega in a suitable tensor power of our logarithmic relative canonical bundle. Such that omega does not vanish at the generic point of our stratum. Oops. And then we can consider well, the weight function attached to this particular choice of pluricanonical form. And this weight function will tell us that the face corresponding to C is part of the essential skeleton. Yeah, so the weight function attached to omega is identically 0 on the face of the skeleton of curly x corresponding to C, precisely because at the generic point of C, our omega will generate the relative canonical line bundle, or at least after our m tensor power. And, well, since omega is a global section of this mth power of the logarithmic relative canonical line bundle, it's going to be non-negative everywhere. So this means that the phase corresponding to C is contained in the locus of minimal values of the weight function, which is part of the essential skeleton. Yeah, so this gives us very strong control over the shape of the essential skeleton. You just have to compute a minimal DLT model and take the dual intersection complex of its special fiber. And so then we can immediately harvest some benefits from this theorem. So corollary, so the choice of a minimal DLT model curly x determines retraction. Yeah, so the construction, which was set up by Kontsevich and Soibelman, which I explained last time, so the construction of the essential skeleton gave you a way to identify the skeleton, which is supposed to be the base of the non-archimedean SYZ fibration, but it didn't give you the fibration itself. It didn't give you a map from the Berkovich space to the essential skeleton. So now that we can identify the essential skeleton with the skeleton of our minimal DLT model, well, we can just use the canonical retraction map, which is attached to this model. So this, in the Calabi-Yau case, this has the expected properties of the SYZ fibration. But it's important to remark that even though the essential skeleton is completely canonical, this map will depend on the choice of a minimal model. So it has the expected properties of the SYZ fibration. In particular, we expect from the SYZ fibration that the fibers are collapsible. So we want to know that this guy is still a strong deformation retract. So when we work with SNC models instead of DLT models, this is a result which is essentially due to Berkovich, which I've explained in the previous lectures. So it's a very deep and highly non-trivial fact that this remains true for DLT models. Or extends to a strong deformation retraction. Always, so not only in the Calabi-Yau case. And so this is due to Tommaso, Collard, and Chenyang. So the idea of the proof is the following. So we start not with a DLT model, but with an SNC model. We form its skeleton, and then, thanks to Berkovich's results, we know that the retraction map to the skeleton is going to extend to a strong deformation retraction. And then we run a minimal model program for our SNC model together with the reduced special fiber. So this is going to produce a finite sequence of DLT models ending in a minimal model. And in each step of the MMP, we can check what happens to the skeleton. And so what the Fernex, Collard, and Xu have shown is that every step of the MMP induces a so-called collapse on the skeleton. So collapse is a particular type of strong deformation retract for finite simplicial complexes. So since the skeleton we started with was a strong deformation retraction of the Berkovich space, and every step in the MMP gives you a strong deformation retraction of the skeleton, we know that the outcome, our essential skeleton, is a strong deformation retraction of the retract of the whole thing. But this is really a highly non-trivial result, and you really have to look closely into the machinery of the MMP in order to prove it.
I'm not sure if I understand the word extend in this context. In extend, I would that it extends to something.
Yes, so the retraction, so the strong homotopy equivalence from the identity to the... So it extends to to a deformation from the identity map on xn to my projection. So that would be xn cross 0, 1 to xn, which at time 0 gives me the identity, and at time 1 gives me works. Yeah. I think there's a lot of confusion about terminology around this stuff, but yeah, according to Wikipedia, this is the correct way to state it.
So when you defined the SYZ fibration at the beginning, you saw some condition in the degeneration.
That's right.
So here, basically, when you see the DC in the Calabi-Yau case, you see the SYZ fibration, that condition does not appear, does not play a role, does it?
That's right. I'm going to show a couple of examples that will make clear where this condition of total degeneracy pops up.
And also, you're assuming that the little omega is semi-ample.
That's right.
That's not a Calabi-Yau case, right?
Sure, because then it's going to be trivial. So in particular, semi-ample. Yeah, so I mean, this construction is way more general than just a Calabi-Yau case. I'm just saying that in the case where we expect a non-archimedean SYZ fibration, this map turns out to have the expected properties, or at least we expect that it has the expected properties. So not everything has been completely proven, but everything we know points in that direction. So let's look at a couple of examples. So assume that the residue field is algebraically closed, and that our canonical line bundle on X is trivial, and that X has semi-stable reduction. Yeah, so the semi-stable reduction is also related to some kind of stabilization property of the essential skeleton. So what happens is that the essential skeleton is not completely stable under ramified base change, but after base change, the Galois group will act on the essential skeleton, and the essential skeleton downstairs will be the Galois quotient of the skeleton upstairs. But once you reach semi-stable reduction, your essential skeleton will stabilize as well. So that's where this condition comes from. And then in low dimension, we can explicitly classify the essential skeleton that appear. So in the case of dimension 1, so we're looking at an elliptic curve, and there are two possibilities. Either the essential skeleton is a point, so this is the case of good reduction. And so in this case, we see that we don't get a very interesting SYZ fibration, because this doesn't tell us anything more about the geometry of the elliptic curve. On the other hand, if we have multiplicative reduction, then the essential skeleton is going to be a circle, which is precisely the skeleton of the minimal SNC model that appeared in the picture that I've shown you last time when I discussed the structure of the analytification of Tate curves. So that's the complete picture for elliptic curves. And then in dimension 2, so there are two cases to consider. So X abelian surface. Then the essential skeleton will be a Cartesian power of S1. And the power is given by an invariant which is called the toric rank. So there are different ways to define a toric rank. It's either by using non-Archimedean uniformization or by using a theory of neuron models. But in fact, the toric rank can also be characterized as the maximal size of Jordan block of the monodromy on the degree 2 cohomology -1. So we get a point S1 or a real two-dimensional torus S1 cross S1. depending on whether the monodromy is trivial as a rank 2 Jordan block or a rank 3 Jordan block. And so we get a similar distinction when X is a K3 surface. So here we are essentially looking at the Kulikov classification of semi-stable degenerations of K3 surfaces. So the skeleton will be a point, again in the good reduction case. Will be a segment for so-called type 2 degenerations. So if we have a Jordan block of rank 2 but not of rank 3, and it will be S2 in the maximally degenerate case. So when we have a size 3 Jordan block of monodromy. And I remember in the maximally degenerate case, according to the SYZ conjecture, we're always hoping to find a sphere of maximal dimensions. So this in particular confirms that this picture is correct for dimensions 1 and 2. The middle case is all the rest. So when I have a rank 2 Jordan block, but not a rank 3 Jordan block on H2.
So wait, when you say this picture is correct, there's also the issue with being Lagrangian.
That's right. So as far as I know, it's not understood yet what is the correct analog of being Lagrangian in a non-Archimedean world. So somehow this doesn't seem to play a role in the reconstruction program. And then, of course, when you see this table, it's natural to ask what happens in dimension at least 3. So here is what we would like to find. So if X is Calabi-Yau in the strict sense, so we want to rule out things like abelian varieties. So we impose vanishing of the Hodge numbers. And we also need to impose that Calabi-Yau is simply connected. Then the SYZ conjecture suggests that the skeleton should be an n-sphere. So recently, Collard and Xu have provided some evidence in this direction. I mean, the results they proved are more general, but they particularly apply to this situation. So this is indeed the case if we are in dimension 3. So under these conditions, the essential skeleton will be a 3-sphere.
Wait, doesn't that good reduction?
I'm still assuming maximally degenerate. I'm sorry. Thanks. So that's important. I'm still assuming that X is semi-stable reduction, and I'm assuming that if I look at the middle degree cohomology, the monodromy action has a Jordan block of maximal rank, being dimension +1. So Collard and Xu have verified that this is indeed the case in dimension 3, and they have some results in dimension 4, assuming that X has a minimal DLT model, which is in fact SNC. Sure. That's right. So there are a couple of things that we can say in any dimension. So in any dimension, we know that if we take the profinite completion of the fundamental group of the essential skeleton, then this is going to be trivial. And the reason is that, well, we know that the essential skeleton is homotopy equivalent to the whole Berkovich space. If the Berkovich space has a finite topological cover, then you automatically also get a finite étale cover of the Calabi-Yau variety X, just by lifting the analytic structure. And since we're assuming that the algebraic fundamental group is trivial, we get the same result for the essential skeleton. And to answer Thomas's question, we also know that the essential skeleton is a rational homology sphere of dimension n.
This seems to fail in dimension 1.
But I'm assuming simply connected. There are no simply connected Calabi-Yaus in dimension 1. And so this you get essentially from Hodge theory. So there's a general result saying that if you have a smooth and proper variety X over K, say that K is a complex Laurent series field, and you compute a singular cohomology with Q coefficients of the Berkovich analytification, what you get is the weight zero part of the limit mixed Hodge structure, which is associated with the degeneration. And so in this case, the condition that X is maximally degenerate and that these intermediate Hodge numbers vanish tells us that limit mixed Hodge structure has the cohomology, the Q cohomology of a sphere of dimension n. And so the same thing is true for the essential skeleton. Again, by the fact that it's homotopy equivalent to the whole Berkovich space. And so these results you can get in a fairly straightforward way. The whole difficulty of proving results like the ones of Collard and Xu is showing that the essential skeleton is a topological manifold. And this is where you need some hardcore MMP, and this also explains why they only got results up to dimension 4. And so it remains a very interesting problem to extend these results to higher dimension. Sorry? That's right. So we don't, in dimension 5 or even in dimension 4 without this SNC condition, we don't know if it's a topological manifold. So what you can show, so this appeared in one of my papers with Chenyang, you can show that it's a so-called pseudo manifold. So this you get fairly quickly from MMP results, but going further requires a lot more efforts. Well, for instance, to conclude that I have some non-trivial cohomology in dimension n, in degree n. Because I want that the weight zero part of the limit mixed Hodge structure is non-trivial. That's right. So you try to understand the dual intersection complex of the special fiber of a minimal DLT model, using all the MMP technology that you can find in your reserve. But yeah, to a sense, what I like to add is, personally, I would be very happy if we could find a way avoiding as much MMP technology as possible to reprove some of the results that I've explained today. Not because I dislike MMP, but because I find MMP more difficult than Berkovich spaces. And because I personally hope that we can actually use Berkovich geometry to say new things about MMP as well, instead of using MMP to prove things about Berkovich spaces. And so here's a hope. Assume that omega x is trivial, and let omega be a volume form. Yeah, so in this case, it's easy to see that in order to compute the essential skeleton, you just have to check for the form omega. So in other words, this is the locus where the weight function attached to omega reaches its minimal value. Yeah, and so here's a slogan that I want to put between quotation marks, because at this point I don't know how to make it mathematically sound. So the idea is that the weight function attached to omega induces flow on the Berkovich space in the directions of decreasing weight. That collapses the Berkovich space onto the essential skeleton. So in particular, we would like to use this idea to reprove that the essential skeleton is a strong deformation retract of the Berkovich nullification. And so one reason to believe in this picture is the example of the Tate elliptic curve. So let me recall what it looks like. So we had the essential skeleton sitting as a circle in the middle of the picture. So here, x is a Tate curve. And then we had these branches sticking out. And so what happens for Berkovich curves is that you can always define a canonical metric on the Berkovich nullification. And so if you endow this Berkovich curve with its canonical metric, and you look at the properties of the weight function on this curve, then you will see that the weight function is constant in the middle. So that's just because of the triviality of the logarithmic relative canonical line bundle on the minimal SNC model. And then as you start moving away from the skeleton, the weight function is strictly increasing with constant slope 1. So this is essentially the only case where we can implement this slogan in a precise way. Just because at every point there's a very small number of directions to choose from, and the weight function is always going to give you the unique direction that leads you towards the skeleton. And so the hope is that we can somehow generalize this picture to arbitrary dimension as well. But part of the problem is that we don't have a good working definition of what it means to be a flow on a Berkovich space at this point. So since we cannot really define this notion yet, with Chenyang we started to think about some properties that should be true if we believe in such a slogan. So in order to provide some evidence, we said, okay, if we believe this, then such and such should be true as well, and let's try if we can prove that. Using the MMP, because we don't have the right Berkovich tools yet. And so we proved two results that suggest that something like this should hold. So theorem A. So the idea is, to work maybe not on the whole Berkovich space, but to start from any choice of SNC model and to look at the properties of the weight function on its skeleton. So let curly x be any SNC model for x. And I'm still assuming that omega x is trivial and that omega is a particular choice of volume form. So the first theorem says the following. So assume that the weight function is constant on a maximal phase of the Berkovich skeleton of curly X. Yeah? So this just means a dual intersection complex of its special fiber. So this poses a problem, because according to our slogan, if we place ourselves at any point of this maximal phase, we should be able to read off from the weight function which direction we need to follow in order to land in the essential skeleton, to meet the locus of minimal weight. And of course, if the weight function is constant on this maximal phase, then it doesn't give us any direction at all. So according to our slogan, this is only allowed to happen if we're already in the essential skeleton. And that's exactly what we proved. No, it just means maximal with respect to inclusion of phases. That's right, that's right. So it just means that it's not contained in a strictly larger phase. And so that's a first result that we were able to prove. And then a second piece of evidence is the following. So we've seen, well, from the results of the Fernet-Scolar and Chu, we get a collapse from the skeleton of our SNC model onto the essential skeleton. But somehow we want to check that this collapse is compatible with the values of the weight function. And so that's what theorem B tells us. So let W be any real number such that W is at least the minimal weight. Then there exists a collapse. And again, collapse just means a particular type of combinatorially defined strong deformation retract of the skeleton of our SNC model onto the essential skeleton that simultaneously collapses the subcomplex and sorry, I realized that I messed up the formulation. So the correct statement is that we don't choose W in advance, we choose W at the end. Okay, so again, using MMP, you can set up a collapse of the Berkovich skeleton of our SNC model onto the essential skeleton. So this is a result of the Fernet-Scolar and Chu. But you can check that this will also collapse simultaneously all the subcomplexes of this form, where W is any real number which is at least the minimal value of the weight function, and where this notation indicates the subcomplex which is spanned by the vertices where the weight is at most W. And so this tells us that we have a strong deformation retract onto the essential skeleton, which is compatible with the weight function in the sense that it also collapses all of the intermediate level sets. We think that theorem A and B are strong evidence for the expectation that something like our slogan should be true. And well, one of the things I'm thinking about right now is how to make this more precise using tools from Berkovich analytic geometry.
So this is not a set of points that has less or equal than W, which W is in relation.
I expect that in the end it won't make any difference, but let's say formally this is defined as the subcomplex span by the vertices where the weight is at most W. Yeah. So it's a sub-simplicial complex of the full thing. But in fact, there's another reason why we were interested in these results, which is somewhat unexpected at first. So we found that this result has interesting applications in number theory, more precisely in the theory of Igusa zeta functions. So let me try to explain in the last 10 minutes where these applications come from. So here we start with a polynomial f with integer coefficients in n variables, such that f vanishes at the origin, but f is not identically 0, and we choose any prime p. And then, using this as input, you can set up an elementary counting problem. So for all non-negative integers d, we define numbers depending on f, p, and d. So this is the number of elements x in pz modulo p to the power d plus 1z to the power n, such that f of x is congruent to 0 modulo p to the power d plus 1. Yeah, so in other words, we're counting the number of solutions of the congruence f congruent to 1 modulo p to the power d plus 1. But we're only interested in the solutions that reduce to the origin modulo p. So it's a way to zoom in around the local behavior of f at the origin. So in number theory, people are interested in the asymptotic behavior of these numbers as d goes to infinity. Well, if you want to understand the asymptotic behavior of a sequence of numbers like this, the natural thing to do is to form a generating series. Whose coefficients are exactly the numbers that we've just defined. Yeah, so somehow understanding the asymptotics of these numbers is equivalent to understanding the algebraic properties of this generating series. But once you've defined this generating series, the first question that comes to mind is whether it's rational. In fact, this question was asked by Borovich and Shafarevich in a textbook on number theory in 1966. And it was solved by Igusa in 1975 using a very ingenious technique. Yeah, so Igusa proved that this thing is always rational. Well, and the proof goes as follows. You rewrite the generating series in terms of a certain p-adic integral. So we integrate over the domain p is p to the power n. And we integrate the p-adic absolute value of f raised to some complex power s with respect to the Haar measure on our domain of integration. So this expression is called Igusa zeta function. Yeah, and so, well, there are some convergence issues with these integrals. So the variable s is a complex number. But in order to guarantee convergence, we assume that the real part of S is positive. And then it's a basic exercise in p-adic integration to understand that knowing this zeta function is equivalent to knowing the original generating series, where we make a substitution t equal to p to the power minus s. So they're not equal on the nose, but there's a very simple transformation rule that allows you to go back and forth between these two invariants. So the problem of proving rationality of the generating series became the problem of proving rationality of the p-adic zeta function in p to the power minus s. And so then Igusa proved that the zeta function is rational in p to the power minus s using change of variables and resolution of singularities. Yeah, so the whole advantage of transforming our generating series into a p-adic integral is that we know that p-adic integrals have a very nice property with respect to birational modifications. It's given by a change of variables formula for the p-adic measure. And so using log resolutions of singularities for the hypersurface defined by f over q, you can actually reduce the calculation to a local calculation in the case where f is a monomial, and then you see right away that it's going to be rational in p to the power minus s. And this actually gives you more. It doesn't only give you rationality, but it gives you some interesting connections between the poles of the zeta function and the invariants that pop up in your log resolution, such as multiplicities and log discrepancies. And so from this, you can, in particular, get the following result. So the computation shows that order of a pole of the zeta function is at most the number of variables. And second, at least if p is sufficiently large, the real part of a pole is at most minus the log canonical threshold of f at 0. So somehow you see that the log canonical threshold of f is going to control the asymptotic behavior of our numbers of solutions of congruences. And in fact, this will be a real part of a pole, at least for infinitely many values of p. And now there was a conjecture by Vez, which was formulated in 1999, which somehow makes a connection between these two observations. So we assume that p is large enough. If S0 is a pole of maximal order, so order n, of the p-adic zeta function, then the real part of the pole is also as large as possible, namely, it must be minus the log canonical threshold of f. And in fact, this is a result that we proved together with Chenyang, which appeared in print this year, by means of a variant of theorem A, for hypersurface singularities. So it turns out that this whole business of weight functions, essential scalata, and so on, can also be set up for hypersurface singularities. And the role of the minimal weight in that situation is played exactly by the log canonical threshold. And so by translating the results, we got exactly the tool that was needed in order to settle this conjecture. And so now I have to look at the chairman. Do I have 2 minutes to explain the proof? It's pretty quick, mainly because I will hide a couple of the technical details. Okay, so let h from y to x, and here, oops, x is a finite space over Q, be a log resolution for the pair consisting of x and the zero locus of f. And then assuming, or shrinking x around 0, we can assume that every stratum of the total transform of the zero locus of f meets the inverse image of 0. Just if this is not the case, then we delete the image of this stratum in x, and we just replace x by a smaller neighborhood of the origin. And then, well, we can introduce the standard notation. So I will denote by y0 this total transform. And so I write it as sum of NIEI. And I write a relative canonical divisor as a sum of nu minus 1 EI, where the nu I are the log discrepancies. And then I can, well, this is a strict normal crossings divisor, so can again form its dual intersection complex. And I can use the multiplicities Ni and the log discrepancies nu I in order to define a weight function. So it's characterized by the following properties. So if I take the weight at a vertex Vi, so this is a vertex corresponding to a component Ei, then I get nu I divided by Ni. And in order to define it on the higher dimensional faces, I impose the condition that it's affine on every face. And now we're almost done. So if you look at Igusa's calculation, it turns out that the only way you can get a pole of order n at S0 is if there exist n different components in a special fiber, which intersect in a point, such that for each of these components, the value nu I divided by Ni is equal to the real part of it, equal to minus the real part of the pole. So if we translate this into a statement about our weight function, this means that we have a face of the dual intersection complex of maximal dimension, n, such that the weight function is constant on this face, and such that the value of the weight function is precisely minus the real part of the pole. And then we prove a variant of theorem A in this context, saying that the only way the weight function can be constant on a maximal face is when the weight is minimal, meaning that the weight is equal to the log canonical threshold. So conclusion, the real part of our pole is minus the log canonical threshold, as predicted by Weiss's conjecture. And that's the end of the proof. I'm sorry I had to rush a bit at the end. I don't want Paolo to get angry with me, so I'll be happy to answer any questions you may have.